Hi, I am SB sir and I will teach you today the kinetics of enzymatic reaction. I will derive the Michaelis Menten equation based on certain assumptions of a enzyme substrate reaction. Now, while we do that, we need to write an equation. And what is the equation? The enzyme reacts with substrate to form enzyme substrate complex, and now this enzyme substrate complex is a particular state of enzyme where this complex has higher energy levels and it can break down to both the free enzyme and the substrate, or it can break down to enzyme plus product. Now I have given an equal to sign here. Why do I give that? So this is a forward reaction and this is the backward reaction. This is the forward reaction for this second reaction and this is the backward reaction for the second reaction. So if we go to the first class and then see that why did I give this two-way arrows? Because every enzymatic reaction follows a two-way reaction, because it does not alter the equilibrium of a reaction. Means it is always the forward reaction as well as the backward reaction, both takes place, but in a little quantity. Earlier it was a very small quantity of the substrate that was changed to product, but now in the presence of the enzyme, much larger amount of substrates get converted to product. At the same time, much larger amount of products get converted to the substrate at the same time. But enzyme, what it does is that it increases the amount in a much lower time. So the equilibrium of the reaction, the enzyme does not alter the equilibrium of the reaction. Equilibrium means this change across this is equal to, this is the equilibrium of the reaction. The equilibrium is not altered. Much larger amounts gets changed to the product. Now if I say that this is the first part of the reaction and this is the second part of the reaction, and we derive at some rate constants. So what are the rate constants? I told you that rate constants are what? For this constants, the rate constant of this forward reaction is, say, K1. Forward reaction, first forward reaction, rate constant is K1. And if I say that rate constant for the backward reaction, I denote it by K minus 1. The rate constant of forward reaction is K1 and rate constant of the backward reaction is K minus 1. Then I tell that the rate constant of this this second forward reaction is K2 and the rate constant of this backward reaction is K minus 2. Now if I say what are these rate constants, if I am repeatedly telling you that these are the rate constants. Rate constants are what? The ratio of the product by the ratio of the reactants. So this is the product for the forward reaction. For the first reaction, this is the product. The enzymes, the formation of the ES complex is the product of this reaction, and these are the reactants. So the rate constant, what is K1? K1 is basically the ratio of the product by the ratio of the reactant. So what is K1? Is equal to ES, the molar concentration of the product by the molar concentration of the reactants. So what is ES? ES. So how much ES has formed? The rate constant will give you K1 into E into S. So if we want to know how much ES has formed, and the rate constant will tell you, the rate constant multiplied by the amount of enzymes multiplied by the amount of substrate will give you that this amount of ES has formed by this arrow, by this forward reaction. So the amount of ES formed is K1 into E into S. Now if we go into the if we further analyze this reaction, this total two-step reaction. In the first step, enzyme substrate complex is formed, and in the second step, the enzyme complex substrate. Now the enzyme acts on the substrate, and after the formation of the complex, the enzyme acts on the substrate and it does certain it breaks certain bonds, it changes certain bonds, it forms a altogether new molecule which is called the product, and it then releases the product in the second reaction. Now if we say that this about the velocity of these two reactions, the velocity of this reaction is slower. The velocity of this reaction, the second part of the reaction, is slower. So this is the slower step and this is the faster step. Binding of the enzyme with the substrate is a very specific thing, and it takes place faster, and the second step is the slower step. So if we consider any reaction, suppose if we consider a real life example, suppose you want to ride a metro. So what you do is that you buy a ticket and then punch the ticket and then go to the station and wait for the metro. Now in these two steps, buying of the ticket and the punching of the ticket, if the second part of the thing, that punching of the ticket, is slower, and the man which is performing the punching of the ticket is very slow at his hands, so what do we say, that there will be a queue in this. So this, if the primary step is fast, the buying of the tickets is fast, and the second step, that is punching of the ticket, is slow, so there will be a queue, people will accumulate there. That happens in case of enzymes also. Means if this step is faster, though the enzyme substrate complex accumulates, and this step is slower, so this accumulation begins, and accumulation is there in the ES substrate, enzyme substrate complex is much more, enzyme substrate complex accumulates, and then this is the slower reaction. Then the second step is naturally slower. So the product release is now somehow differed, and it will, so the total reaction, then at some point of time you have given the substrates with the enzyme, you have exposed the substrates with the enzyme. So you are eagerly waiting when the product will form. So I say that okay, the product is now getting formed, because the product is now delayed, because the enzyme will now act on the substrate and it will release the product. So it will depend on the second step. So it will depend on this. It will depend on this rate constant. Rate constant is what I told you, the product by the reactant. So it will depend on this rate constant, the ratio of the product and reactant of this second reaction, and this is called the K2, and this rate constant is called the turnover number. So this is actually a ratio of the this product of this reaction and the reactants, product by reactants, and this is called the turnover number. It tells us, the K2 tells us how fast the reaction. If this turnover number is higher, so the reaction is faster. If the turnover number is lower, the reaction is slower. So this K2 is actually the much important step, and here it is the second step of the reaction, and it is of much importance, because the whole reaction kinetics depends on this second slower part of the reaction. Now we need to know a little bit of some assumptions while we derive at the Michaelis Menten equation. So what are the assumptions? There are three assumptions while we derive in the Michaelis Menten equation. What are these three assumptions? The first assumption is the steady state assumption. The second assumption is the Vmax assumption. and the third assumption is the initial velocity assumption. Now I will explain what are these three assumptions. Steady state assumption tells us that any enzymatic reaction, while it goes on, it actually happens that the enzyme substrate complex is formed in a steady state way. In a steady state way means if this is the first reaction and this is the backward reaction, the enzyme at steady state, the rate of formation of ES, the rate of formation of this ES by these two reactions, the reactions by which ES is formed, this forward reaction and this backward reaction, and the rate of breakdown of ES. The rate of breakdown of ES is, this is the backward reaction and this is the forward reaction by which ES is breaking down. ES is breaking down by the outside arrows. Here the outside arrow, the K2, and here another outside arrow from ES, it is the K minus 1. And the inside arrows towards ES is the rate of formation of ES. The rate of formation of ES, these arrows determine the rate of formation of ES, that is this K1 and this K minus 1. These two arrows balances each other, means steady state, at steady state. So what is steady state? If we say what is steady state, this is a steady state. This part of a figure is a steady state. So these are the different steady state. If this is a maximal steady state, Vmax, there are submaximal steady states also. But all these steady states, submaximal steady state 1, SS1, submaximal steady state 2, at much lower steady state, but all these are steady state, means the curve gets flat. This is the steady state reaction. At all the steady states, the rate of formation of ES is equal to the rate of breakdown of ES. So this is the state of steady state assumption, where we assume that in a reaction after a certain point of time will go into a steady state where both the forward reactions and the backward reactions will balance, and the molar concentration of ES will remain constant over time. The molar concentration will remain constant over time. And what is this molar concentration? Why it remains constant over time? Because the rate of formation of ES and the rate of breakdown of ES is equal. The rate of formation of ES and rate of breakdown of ES is equal. So I write the steady state assumption as, at steady state, rate of formation of ES of ES complex is equal to rate of breakdown of ES complex. Now I will go to the second assumption, that is the maximal velocity assumption. What is the maximal velocity assumption? At maximum velocity, any velocity of this enzymatic reaction will depend on K2, because K2 is the slower step. This is the slower step, and this is the K2 is the turnover number. It will determine that the slower step will determine how much amount of product is formed. So what is the Vmax assumption? We can know that a little bit from this from the name of this assumption. What is Vmax? It gives an estimate of Vmax. So what is Vmax? Vmax is K2 into, like just like this one. What is the amount of ES that is formed? K1 into E into S, K1 into E into S, the rate constant into the reactant. So what is the Vmax assumption? Vmax is equal to K2 into the reactant, K2 into the reactants, K2 into ES, K2 into ES, and at Vmax this velocity is equal to K2 into ES. And at Vmax, if I write Vmax here instead of velocity, we have to write K2 into ET. Now this is a new term, ET. What is ET? ET is the total enzyme. That means the enzyme, this is the enzyme bound with ES, the enzyme bound with substrate. And here I write ET, means the total enzyme that is present in the reaction. And we assume that at velocity maximum, the enzyme that is bound to substrate, is the total enzyme. That means the total enzyme that is present inside the cell or inside the test tube is now acting and continually changing, is now bound to the substrate, and acting on the substrate and continually changing the substrate into product and releasing the product. And so what is the Vmax assumption? The Vmax assumption is Vmax is equal to K2 into ET. Vmax will always be equal to K, well, any velocity of an enzymatic reaction will always be equal to the K2 into the amount of ES. K2 into the amount of ES is any velocity of an enzymatic reaction. Let it be final velocity Vmax, let it be initial velocity. Any velocity will depend on K2 into the amount of ES. But at what is the Vmax assumption? Vmax assumption is Vmax is equal to K2 into ET. That means the total enzyme, instead of ES, we write that it is ET. That is the total enzyme that is present in the reaction or in the cell is now acting on the substrate and producing the product. Now, what is the initial velocity assumption? I will go into the third topic. What is the initial velocity assumption? Initial velocity assumption is at V0, it is K2 into ES, it is K2 into ES. At V0, it is equal to K2 into ES. That means when the it is the initial velocity assumption. That means in the first few milliseconds of the reaction, when the reaction has just started, it is the amount of ES. It is the amount of ES that will tell us that how much product is formed. It is the amount of ES that will tell us how much product is formed. It will absolutely depend on the amount of ES. So V0, initial velocity V0 is equal to K2 into the amount of ES that is formed. So these are the three assumptions. The steady state assumption, which tells us that at steady state, rate of formation of ES complex is equal to rate of breakdown of ES complex. At maximum velocity, at the Vmax assumption, where Vmax is equal to K2 into ET, and the initial velocity assumption V0 equal to K2 into ES. So these are the three assumptions, and with those three assumptions, keeping in mind these three assumptions, I will go into the derivation of Michaelis Menten equation. Now I will go into the derivation of Michaelis Menten equation, writing these equations as this equation as equation 1, this as equation 2. So I will just write it down in this, and at this side V equal to K2 into ES. Before rubbing this board, V equal to K2 into ET. This is the Vmax is equal to K2 into ET. And V0 equal to K2 into ES. Initial velocity assumption. Now I will go to the derivation of Michaelis Menten equation with the three assumptions that I have just told you. Now I will go to the derivation of Michaelis Menten equation. Then with the first assumption, that is rate of formation of ES is equal to rate of formation of ES equal to rate of breakdown I draw a mathematical relation of the rate of formation of ES and rate of breakdown of ES. Now I will derive with the mathematical expression. So how is ES formed? ES is formed by this reaction, this forward reaction. ES is formed, and ES is formed here at this backward reaction. This backward reaction, the enzyme and product reacts to form ES, and here the enzyme and substrate reacts to form ES. ES is formed by these two equations. This is the free enzyme. This is the free enzyme that is reacting with substrate. I have told you that there are three types of enzymes that is present. One is the free enzyme, the enzyme bound to the substrate, and this free enzyme and the enzyme bound to the substrate gives you the total enzyme, the ET. So what is ET? The total enzyme. It is the free enzyme plus the enzyme bound to the substrate. Now the rate of formation of ES. What is the rate of formation of ES? Rate of formation of ES is equal to K1 into E into S, K1 into E into S. This is the forward reaction, and K minus 2 into E into P plus K minus 2 into E into P. And rate of breakdown of ES, rate of breakdown of ES, rate of breakdown of ES, see this arrow is the breakdown. So this arrow K minus 1 into ES, K minus 1, what is the rate of breakdown? Means the formation of E into S. Just now I told you, when I write the product, that it is the K minus 1 into ES, K minus what is, so the breakdown, this breakdown arrow, K minus 1 into ES. And what are the other breakdown pathway? K2 into ES plus K2 into ES. This derivation that I am just drawing, I am giving you, is from Leninger. So you can follow the book Leninger. You can read that book, and you will find that the derivation there also. Now I will tell you about this. I will just concentrate on a little bit thing here. Little bit here. So this is the free enzyme. What is free enzyme? It is the total enzyme minus the enzyme that is bound to substrate. What is free enzyme? It is the total enzyme. I have seen that it is at the total enzyme, that there is an amount of enzyme that is present in the cell, the odd that I have provided in the test tube, that is the total enzyme, minus the enzyme that has reacted with the substrate, the enzyme bound to the substrate. This E is equal to EF, or the free enzyme that reacts with substrate. So K1 into E into S is actually K1 into E, that is the free enzyme that is reacting, and into S, plus K minus 2 into E into P, that is this reaction, K minus 2 into E into P. This is the rate of formation. These are the equations of formation, and these are the expressions for breakdown. So rate of formation of ES is equal to rate of breakdown by this 2. Now I will go into K1 into deriving this part, into breaking this part. It is K1 into this E free is ET minus ES into S plus K minus 2 E into P is equal to this part K minus 1 ES plus K2 ES. Now in the initial part of the reaction, product is equal to 0. So this part can be safely ignored, because in the initial part P is equal to 0, and this equation, this expression can be ignored. this expression can be ignored. So the equation now turns as p is equal to 0, we just consider this part of the equation and this part of the equation. So if I write this equation now in multiplying these factors and see what happens. K1 into Et into S minus K1 into Es into S equal to, I ignored this part, K minus 1 into Es plus K2 into Es. So I have Es in this 3 equation. Here I have Es. So I have Es in these 2 parts. Es here, Es here, and Es here. So if I put all the Es things on one side of the equation, so if I do that, what it becomes, and I take this Es out of the equation. So I take this Es out of this equation. Es is Es, what it remains here, K1 into S. Here what remains, K minus 1. Here what remains, K2. And I have taken Es out of these 3 equations. Out of these 3 equations, from this equation I have taken out the Es. From this equation I have taken out the Es. From this equation I have taken out the Es. So these 3 reactions I have taken out the Es, and what it is equal to, K1 into Et into S. Now I say what I do is that I just put this K1 S part here. Okay, I just put this K1 here. So I rub out K1 from here, I rub out K1 from here. So the equation changes like this, Es K1 into S plus K minus 1 plus K2 by K1 is equal to Et S. So K1 cancels, and there is a constant term that is here, and I tell that this constant part is Km, the ratio of this rate constant, I tell it as Km, and I rewrite this equation as Es third bracket S plus Km equal to Et into S. Now what is Et? If we refer this equation, what is Et? Et is equal to Vmax by K2. I write it here. Et is equal to Vmax by K2. Vmax by K2. Now what is K2 into Es? K2 into Es, if I write this, if I see this equation, K2 into Es, K2 into Es is what? Velocity. The velocity of an enzymatic reaction. So this, instead of writing Es and K2, I write it here. I rub out K2 from here. I rub out Es from here. I write velocity. The velocity from this equation. Velocity is equal to K2 into Es. So I write velocity. So what velocity is equal to? Velocity is equal to velocity into s plus km equal to Vmax s, or velocity is equal to Vmax s by this part by km plus s. So what is this? This is the Michaelis Menten equation. So just replacing a few terms from this rate constants, I have just replaced a few terms, this two assumptions, from these two assumptions I just replaced a few things. I just cancelled out this portion. I just assume that the total enzyme minus the enzyme substrate complex is the free enzyme. I just ignored this equation, and what I have done in the primary thing is that in this how did I form this equation? That is the initial, the steady state assumption. The rate of formation of ES is equal to rate of breakdown of ES. Rate of formation depends on K1 into E into S. Rate of formation depends on K minus 2 into E into P, K minus 2 into E into P. Rate of breakdown depends on K minus 1 into ES, K minus 1 into ES. And this is another breakdown, depends on K minus K2 into ES, this is K2 into ES. I have ignored this part. This part is K minus 2 into E into P, K minus 2 into E into P, as initially the product is 0. So I have ignored this part of this equation, and I have added another step here, that K1 into E into S, K1 into E into S is actually, here E is the free enzyme that is present, the E is the free enzyme, that is EF, and EF is equal to the total enzyme minus the enzyme that is reacted with the substrate. I have just write it down. I have just simplified this equation, K1 A1 ETS, K1 ETS, K1 ESS, K1 ESS. Here it remains like this, K1 ES, K1 ES, here remains like this, K2 ES. Then what I have done is that I just took out the ES as common, this ES part from here and from here as common, and K1 ES remains, K1 into S remains here, and K minus 1, K2 from these two expressions, K minus 1, K2. And what I did is that I just, here the K1 was there, and I just put it down there, and I rubbed it out, this K1. I rubbed this K1 out of the equation, and I just put that in here. So the equation changed as, and I just shared equally K1 and K1 with this, and this forms the Km. This is the expression of the Km, the K minus 1 plus K2, K minus 1 plus K2 by K1. This is the Km part, K minus 1 plus K2 by K. K minus 1 plus K2, you have to remember this is very important. K minus 1 plus K2 plus, I draw a plus here, K minus 1 plus K2 by K1, K minus 1 plus K2 by K1. This is the second kind of definition of Km. That means it is the addition of the rate constants. The rate constants K minus 1 plus K2 by K1 is the Km. It is, I replace it by Km of the reaction. So it becomes Km plus S, that this part of this equation becomes Km plus S, and this ES here, how did I cancel out this ES part? Because I knew that if this ET part is being replaced, this if I consider the previously derived equation, this ET part could be replaced by Vmax by K2. The ET part could be replaced by Vmax by K2. So what I did is that I replaced this ET part by Vmax by K2, and K2 into ES. I got that ET part, from that I got back Vmax by K2, and from this K2 into ES, from this K2 into ES, ET part I replaced, this ET part I replaced by Vmax by K2, Vmax by K2, and from this K2 into ES part, I wrote velocity, I wrote this velocity part. This velocity came from K2 into ES, this two terms, K2 into ES. I wrote the velocity part. So velocity becomes, and the Vmax remained, velocity becomes this expression. We got this expression, final expression, velocity is equal to Vmax into S by Km plus S, Km plus S. So at the end of this class, I have revised you the whole thing. How do we derive? What are the three types of assumptions? The Vmax assumption, the initial velocity assumption, this is the Vmax assumption is equal to K2 into ET. This is the velocity assumption, that it will always, any velocity of an enzymatic reaction will always depend on the turnover number and the amount of ES. This is the turnover number assumption, or you can say it is the velocity assumption. And the first assumption is any reaction kinetics in enzymes follows a steady state, that means at which rate of formation of ES is equal to rate of breakdown, because every reaction reaches a steady state, and at steady state the rate of formation and rate of breakdown becomes equal, and then I draw these mathematical expressions of this steady state, rate of formation these two expressions, rate of breakdown these two expressions, and then I treat that equation and finally derive that this Michaelis Menten equation, equation, Michaelis Menten equation, which is a very important equation. The derivation is also very important, and unless and until you know this derivation, you will not be knowing all the intricacies of the intricacy of this part, the Km part, and the intricacies of other questions that will come in the next part of your career after you graduate or postgraduate. So other the questions that will be coming from this part of the thing is that apart from derive the Michaelis Menten equation, there will be other very deep questions which you will have to know. Other than this derivation part, you will not be able to answer any of that part. So the derivation is very important. Michaelis Menten derivation, you have to know it by heart, you have to learn it by heart, you have to practice it out very thoroughly, and then go to my next class, which is I'll teach you in the next class. I'll teach you about the inhibitions, the different inhibitions of enzymatic reactions, the inhibitors, how the inhibitors inhibit the enzymatic reactions. I'll teach you that part, and I'll also for that part there also I'll need all your help, because I'll need all your revisions from these two classes, so that you become ready for that inhibition part, the competitive inhibition, the uncompetitive inhibition, and the non-competitive inhibition or the mixed inhibition. I'll teach you about those inhibitions in the next class. Before that, you have to primarily know and practice it out, all these things. Thank you.